This chapter we will learn about combinational circuit. We will learn about the bubble pushing concept and compound gauge and some of the logical effort example. And we will also care about the input ordering and also designing a symmetric gauge for some time we want. And we'll also talk about the skewed gauge and the best PN ratio as well. This is one example of the multiplexer you want to design. So it has the input selection signal and D0 and D1 and output Y. This is the assign statement that is used in Verilog. So Y equal to depending on S. If the S is true, then we pass the S1. If the S is false, then D0 is passed. We can simply sketch such a design multiplexer using AND or NOT gauge. As shown here, this AND gate, 2 AND gate and 1 OR gate will do the job here. For the actual circuit, we will implement that AND gate with a NAND gate plus inverter, right? Also, OR gate will be implemented with NOR plus inverter there. If that is such a multiple stages, we can simplify such logic by some bubble pushing technique. So let's go through the bubble pushing technique. First, we have to design some NAND or NOR. We have the multiplexer circuit by having the bubble internal at the input. You see the same logic, right? From this on the right hand side, that logic can be converted using bubble technique, right? If you change the input and output polarity, we change the shape. So that's the same as the circuit. So all the logic can be implemented using NAND gate, 3 NAND gates. The bubble pushing technique, the most useful thing is that the NAND gate can be converted like this, bubble with the NOR, and NOR gate can be put some bubble at the input and output and change the shape, right? This is the De Morgan's law. We are visualizing the circuit transformation graphically. So for the given circuit, we can easily change like this. A can be converted to B, and B can be converted can be C, and C can be converted to D. So all these are the same, right? And finally, this guy is NAND gate. NAND gate, right? Now let's move on to another example that use one compound gate and one NOT gate, the inverter. In compound gate, we have this kind of a combination of the several logic. It is the A or AND and OR inversion, right? This is the AOI circuit with the 2 input for 4 inputs, right? And 1 inverter like this. So this is one other example of the compound gate implementation. So compound gate we can construct like these. For example, AOI 2-1, we have 2 input AND and 1 input OR gate and inversion. And also we have AOI 2-2 and more complicated logic. So for inverter and compound gate example we have. So complicated the logic can be implemented in one stage that is called the compound gate, right? So if you calculate the logical effort for A, for example, here, the input capacitance of the A is 6, so, and the equivalent driving strength is the same as the inverter, like this. So logical effort is 6/3, like that. We can find the similarly the logical effort for all the other the inputs shown here. So once you complete the compound gate, you can calculate the logical effort as shown there, right? Now let's look at another example. The multiplexer has a maximum input of a capacitance of 16 units on each input. It must drive a load of 160 unit cap. Let's estimate the delay of the NAND gate and the compound gate design. We will compare two design choices and see which one would be faster for the same input and output condition. So this is the two different example. One uses the NAND gate implementation, the other one is AOI and inverter compound gate implementation. So we know that H is the path electrical effort. The output load is 160 C and input capacitance is 16. So total H becomes the 10. What about the branching effort? The branching from one input to output is just equal to 1 because it all goes to a single gate, right? And also number of stage for those two cases is 2, right? This one, the other one, and this is the one and the other one. So this is like just an NAND gate, right? First, the NAND gate solution, let's look at it. So parasitic delay is, first one is 2, right? And second one is 2. So total 4 is the parasitic delay. What about the logical effort? Logical effort is 4/3 for NAND gate, so times 4/3, so total path logical effort is 16/9. So F path effort is GBH. We are using this, we are calculating this to find the optimum stage effort. So GBH now become 160 divided by 9, right? So G becomes 16/9 and B equal to 1. H was was it like some value, right? We found that the H previously, so we put that number. So the optimum stage effort becomes nth root of F becomes 4.2. Once we know that 4.2, we can calculate the total output, the total path delay. That will be n number of stage times optimum stage effort plus parasitic. So total it becomes 12.4 if we calculate that. We can remember this number, 12.4 for the NAND solution. What about the compound gate solution here? Let's take a look at. For the compound gate, the parasitic, this parasitic delay is 4. Parasitic effort is 4, and for inverter is 1. So total it becomes 5. Logical effort for this is, the first one is the 6/3 times 1 for the inverter. That becomes the past logical effort equal 2. Now we can calculate the F. That becomes GBH. That comes out 20. If we take the nth root of F, then we get the 4.5. So finally, total delay, minimum path delay would be n times. That is 2. F hat is 4.5 plus 5. That comes to 14. That would be optimum. So compare this number with the 12.5, right? So what you can see is that the compound gate implementation is slower than the NAND gate solution, right? If you care about the speed, you can just simple 2-input NAND gate and try to optimize it using that. Now then, what's the benefit of using the compound gate? We haven't seen this so far, but the benefit of using compound gate is just low power, because it has only 2 switching nodes internally, 1 and 2, right? And so later we will see the calculate the dynamic power consumption. So dynamic power consumption comes from the switching activity on the parasitic or load capacitance, right? So far we know that we can see that in terms of speed, just NAND gate implementation is faster than compound solution. So once we found the F hat, the optimum stage effort, so for the NAND gate implementation, we found that F hat is what, 4.2, right? And for the compound gate implementation, 4.5, right? So using this number, we can determine the gate size. Assuming that we have a 160 output load capacitance and input is only 16. The output is 160, same, right? 160 and input is 16. So using this number and input and output capacitance information, we can size all the transistors. Here we do this calculation from backward, right? So how we determine the 25? That's gonna be, so starting from the load C out times G divided F hat. That comes in C in, right? That becomes the C in. So we know that the F hat is F equal G times H, right? H is electrical effort. So we derive, using that information, we can calculate the input capacitance, that is 50. So for the NAND gate, we know that 1:1 PN ratio, so 50 become equally spread it. So 25 and 25. Once we found this number, we know that the load for the first stage become the 50. So also we do the similar derivation for the first stage. That will give us a total 16. Right. So we know that the input capacitance condition just 16. So we just without calculating this F hat equation, so we know that this maximum input capacitance is 16. So NMOS it becomes 8 and PMOS becomes 8, right? For the compound implementation, we do the same equation. So 160 times, this is the inverter, so 1 G equal 1, and 4.5 is F hat. So finally 36 is the input capacitance, so 16. So 1 to 2, the ratio we can determine that is 24. PMOS is 24 most edge 12. So we know that now this is the 36. For the input capacitance must be 16. So for any input, so for example A and A, the total should be 16, right? So we get this device size.